Welcome to this video. I'm going to be talking about the Seq2Seq model. Now, before I get into the technical details, I'm going to be talking about some of its applications. So there's text translation, right? Translating languages. Text summarization, condensing long documents into brief summaries. Speech recognition, converting audio signals to text transcripts. Image captioning, generating textual descriptions from images using CNN plus Seq2Seq. Chatbots and dialogue systems, generating responses in conversational AI. Video captioning, describing actions in video frames over time. And question answering, generating answers from context passages. Now I'm going to be going over a text translation example in this video. So I'm assuming in this video you'll understand LSTMs. If not, go check out my previous video, LSTMs Explained. So recall from long short-term memory, we have inputs, and then we have these LSTM cells, right? And then if we wanted to translate, I'm going to the store into another language, let's say Korean, we would have the following, right? So I would be 가게에 가고 있어. So it's like I'm going to the store is going to be translated into 3 Korean characters, okay? And then the rest are going to be blanks, okay? So you could see that there immediately, there's a mismatch. And there's a one-to-one mapping, which leads to problems, okay? So we're not going to be able to use a long short-term memory in a translation task, right? Also, another issue is that the further it goes out, basically, errors kind of enhance. So like the longer the sentence or it becomes a paragraph, errors could get amplified, okay? So that's another major issue. Now, there's a paper written by people from Google called Sequence-to-Sequence Learning with Neural Networks. And what it does is that it basically takes a multi-layered, long, short-term memory to map the input sequence to a vector of fixed dimensionality, and then another deep LSTM to decode the target sequence from the vector. Okay, so there's basically an encoder and a decoder. Now the encoder, H is the hidden state. That's something that you should be familiar with from understanding LSTMs, right? And C is the cell state, and which is the long-term memory, the conveyor belt, so to speak, which we also saw in our LSTM video. And they're outputs of the LSTM cell. So we've got these states. And then we've got outputs, right? So it's HOCO is the initial state that we start with. Usually it's randomized. And then the far right in the middle, H6C6, that's the output. So that's the final output vector. And there's 2 context vectors, right? H6 and C6. So it's going to look something like this, but there's going to be about 512 numbers in each. So that's the encoder. Now the decoder. So the decoder doesn't start from scratch. It starts with the context vector that was generated by the encoder. So we saw the H6C6 earlier. And that's what we're going to start with, right? That's our initial state. And it's going to output HDEC1, CDEC1, right? Then you're going to plug that into the next LSTM, HDEC, CDEC1, right? And it's going to output DEC2, DEC2, HDEC2, and CDEC2, right? And so forth until we get to these four. Now let's put it together, right? The encoder and the decoder architecture. I am going to the store. Okay, we've got the H6C6, which is the context vector. Then we're going to plug that into the decoder LSTMs. To pronounce the Korean character, it's kage-e, and then it's kago isa. Okay, so I'm going to the store basically in Korean. And then we got HDEC4, CDEC4, and then the end token. Okay. So that solves the problem with the one-to-one matching. But Seq2Seq also has limitations. So the context vector is compressed into 512 numbers, right? Which I said earlier. But there's multiple vectors, right? That consist of 512 numbers, right? We're not using valuable information, right? The 512 numbers for every hidden state. Okay. So we're kind of throwing that all away and we're just using that one context vector. So attention solves that problem, right? Because it's going to look at all H hidden states. And that's going to be another topic for another time. Thanks for watching and have a great day.